All right, so we're gonna get started, guys. There is a ton of material, so we're gonna be here. I'm going to assume probably about 2 hours. If any of you ever need to leave during it, that's fine. This entire thing is gonna be uploaded to YouTube. Um, you can always just come back, try and find it, see where you left off, stuff like that. If you have any questions, feel free to just ask. I'll be happy to go over them. Um, and so, yeah, without further ado, let's just jump into it. So we're going to go all the way back to square one. So I'm going to try and go through a lot of this stuff that's just been built upon pretty quickly to try and just get through all the material since there is so much. So I'm just going to assume that you guys know what cases and variables are. Case is experimental unit from which data are collected. A variable is a characteristic that's measured and takes on different values. All this stuff. It's stuff that you guys need to know because it will be stuff that they're going to assume that you know on the final. And so just want to make sure that you guys have everything hammered down before you go in for it. So categorical versus quantitative. So categorical is, basically just more or less names that doesn't really have any numbers associated with it. It doesn't really have to have an order, or it could have an order, but the order just doesn't have anything to do with numbers. And quantitative is just numerical values that are placed into a meaningful order so that they can be, kind of like put into a set place. So they have nominal with the categorical. That basically means they have no logical order whatsoever. Or you have ordinal, so it has logical order. It's just not put in a numerical way. There are no numbers involved. So for quantitative, you have a discrete, which is basically like a set value. It just doesn't. It's simply like one number and nothing else. Or continuous, they're like, it can go on for like a few decimal places. It can just go on a little bit more than just being a discrete. So explanatory and response variable. So explanatory variable is something that explains what happened to the response variable during an experiment, otherwise known as the independent variable. The response variable is basically the outcome after the manipulation of the explanatory variable, and that's known as the dependent variable. So population parameter versus sample statistic. The parameter is used when talking about the population as a whole. It's what you really use to make all these generalizations, stuff like that. The statistic is used when talking about a very small sample. And so, just some examples. For mean, you got the population parameter of mu and the sample statistic of x bar. For proportion, you've got the population parameter of p and the sample statistic of p hat. So simple random sampling. It's a method of obtaining a sample from a population where every member has an equal chance of being selected. It's completely random, and the sample is also selected without replacement. Convenient sampling. So basically, it's just not random, so it's not always as good, but it's just the easiest way to just randomly pick a sample. Well, not randomly, but just to quickly get a sample going so that you can use really quickly. It's the easiest way, but again, you can't really use that you can't use the results to make any generalizations since it's not representative of the population. Biases, so you've got the non-response bias. So that's basically just someone who chooses not to participate or someone who chooses to participate. If there's a certain way where someone all right, basically think of it as kind of like a survey. Surveys are completely optional. I'm sure you guys got one to probably fill out about the tutors here at GSG. I'm sure you guys got one to fill out about your teachers. And so answering a survey is completely it's completely up to you. However, generally the most people who do the surveys are people who feel really strongly about a certain way. So it's either going to be the people who feel really strongly oh, they did such a great job, it was so great, or the people who feel really negative and oh my god, they shall be fired, they're terrible. You get very little kind of in the middle, so that just kind of affects your outcome, because there's probably plenty more people who are just not as don't feel as strongly about the subject, you just don't reply. Then you also have a response bias, where it's basically participants to kind of like fit in with the social norms, or because they don't want like upset someone, they want to like kind of tell someone what they want to hear. They don't respond truthfully. So example of this is saying that you didn't drink as much alcohol as you did, saying that you studied more for exam than you did, just something that like aligns with the societal norms, or you think it's something that the researcher wants to hear. So types of studies, you've got experimental. So this is a study where you actually kind of like change the treatments to see the effect. This is also the only one where you can kind of like make a cause and effect, saying that this does cause this, or this has a correlation in this. That's the only one where you can make that claim. You also have observational. So that's basically a study in which a researcher just collects data from the environment, so they're not manipulating anything. You have confounding variables. Sometimes they're also called third or lurking variables. So basically, those are variables that kind of like it affects the outcome, even though it's not supposed to. It's not really anticipated being there. It's more so a problem with observational studies than it is with environmental, and that's kind of why you can't use observational. So an example of this is increase of sales of ice cream with an increase of shark attacks. That's not saying that ice cream leads to you getting attacked by a shark. It's more likely that this is happening in the summer where there's more people in the water. So there are more people out there buying ice cream, but then there are also more people out there in the water for sharks to attack, and there's more likely a chance that sharks are around. So it's kind of like you always just have to be aware of that it could cause an issue when you're doing a study. So you have the types of groups. So you have independent, so they're just completely unrelated to each other, or you have paired, where they're matched in some way. This is also kind of like called match pairs. An example of this is kind of like your exam scores for your midterms and your final. You can kind of assume based on someone's midterm grade, you can kind of like predict their final grade. So blinding, this is a way to try and prevent biases, stuff like that. So you've got the single blind, where one group does not know what treatment they're getting. This is generally the participants. I guess you could do it with like the researchers being the blind ones, but it doesn't really make that much sense. You have the double blind, where neither group, the participants or the researchers, know which treatment they're getting. You have the control group, where basically they don't receive the actual treatment. They either get a placebo or they get nothing. A placebo is something that appears to be an active treatment, but does not actually contain active treatment. An example of this is kind of like a sugar pill instead of like some other kind of pill. Just like people think that they're getting some kind of treatment, but they just don't get it at all. Just to see how much they change just based on getting nothing. All right, so with that, we're going to go into review one. I'm pretty sure we have 25 questions, so I'm trying to get you guys as much possible like experience with questions that might be on your final as possible. So this one's just asking, what is the explanatory variable in this case? So I'll give you guys a little bit of time to answer this, and then we'll keep going. All right, yeah, good. Seems that you guys aren't too shaky on this whole material. So, yeah, it is the IQ scores, since they're using the IQ scores to predict what the grades are going to be at the end of the semester. So, good job, guys. So next up, which of the following is not a quantitative variable? I'll give you guys a little bit of time to answer this one. All right. Yep, it's a t-shirt size, since that's normally listed as being small, medium, large, whereas everything else is generally listed with a numerical value. So, all right. So we're moving on. One categorical variable. Use proportion to summarize data concerning this. So proportion is simply number in the category divided by the total number. Symbol is p hat, all that stuff. Their proportion also has to be between 0 and 1. So risk. I know this was an issue that a lot of people kind of had. So it's basically the probability that event's going to occur. So it's the number with the outcome divided by the total number of outcomes. So for example, just like this flu example, so say 103 children out of 1,000 get the flu each year. So that would be 103 divided by 1,000. So you get about 10%. So about 10% of children get the flu each year. Not to be confused with odds, which is comparing the likelihood of event happening versus the event not happening. So it's basically, it has two different formulas. It only really makes sense to use formula 2 with the risk divided by 1 minus risk if you've already had to calculate the risk, because if not, then it's just an extra step of calculating that and then using that equation. I think the easier one to use is just the number with the outcome divided by the number without the outcome. So continuing with the flu risk, since I already had that up, it's just 0.103 divided by 0.897 to get that number. So then basically the odds of a child getting the flu is 0.115 to 1. All right, so visual representations, one categorical variable. So you can either have a frequency table, a pie chart, or a bar chart. These are the most common ones. I just found these images randomly online. So two categorical variables. Sorry, this is a little cut off, but you basically use a two-way table. Right, and probability. So I don't expect that they're going to test you too heavily on this, but we're still going to go over it nonetheless, because I know it's something that was tricky early on, and I don't want any of you to ever be caught up on something that, So anyway, basically probability, that's just saying that the probability of event A is going to occur. So this number in group A divided by the total number, again, can only be between 0 and 1. So basically, if it's a 0, that's impossible to happen. If it's a 1, that's guaranteed to happen. All right. So disjointed and independent events. So disjointed basically says that events that will never occur at the same time, they are mutually exclusive. And so an example of this is class standing. You can't be both a freshman and a sophomore at the same time. As soon as you graduate from one, you become the other. Independent events, they're basically like unrelated events. So the outcome of one does not affect the outcome of the other at all. So think of birds on city traffic. The more birds you have doesn't really affect the amount of traffic in a city. It's just unrelated. So combination of events. This is a nice little table about all this. So you've got intersection is the probability of A and B, union, the probability of A or B. I know that for the equation previously, it's kind of weird and confusing. That's the reason for that is because you also have to subtract the possibility of A and B. So you basically have, A or B minus A and B. All right, so you have complement. So it's the probability that you won't get A. And you have conditional, which is the probability of A given B. So basically it's saying that A will happen given B happens. Outliers, they're always an issue. We've talked about them to death before. Basically, it's just an observation that falls outside the general scope of observations, and it can really skew your data. Shape, so you always want to try and have a symmetrical distribution. This distribution that is similar on both sides of this, the center. You want the normal distribution, mean equals 0, standard deviation equals 1, bell-shaped. Of course, you always have the asymmetrical ones, which are skewed. So it's considered skewed if the values are more spread out on one side distribution than the other. So you have left skewed over here, and you have right skewed over here. Remember, just follow the tail. That will tell you, what way the skewness is, and we're going to go into, so for left skewed, I just want you guys to like picture the graphs if they ever ask you a question on this, because the mean is going to be less than the median, which is going to be less than the mode, and that's going to be the opposite for right skewed. The mode's going to be less than the median, which is going to be less than the mean. Meanwhile, if it was symmetrical, then they should all be equal. So measure of central tendency. I'm sure you guys all know this. Again, just going over it just to make sure. So the mean is the average, the median is the middle distribution, and the mode is the most frequently occurring value. And so we just went right over this. Again, mean is equal to median, which is equal to mode. If you're in a symmetrical graph, if it's right skewed, then the mode is going to be less than the median, which is going to be less than the mean, and less skewed, the mean is going to be less than the median, which is less than the mode. So empirical rule, also known as the 95% rule, it states that 95% of all observations will fall within 2 standard deviations of the mean. Yep. Just to make sure you guys all know, 68% of the data will fall within 1 standard distribution, 95 will fall within 2 standard deviations, and 99.7 will fall within 3 standard deviations of the mean. There we go. So z-scores used to describe one observation in relation to the distribution of other observations. So a z-score is just your original value of x minus the mean of the original distribution divided by the standard deviation. So you get your z-score. And so review number 3, I'll give you guys a little bit of time to go over this. Just asking for you guys to find the z-score. So I'll give you guys a little bit of time. All right, yeah, you guys got it. To anyone that's a little confused, sorry, this isn't the best. That should be like all of it's divided by the standard deviation. But yeah, it is 1.4 because you take 62 minus 55 divided by the standard deviation of 5, and you end up getting 1.4. All right, so percentiles. It's proportionate distribution less than a given value. So think of test scores. If someone scores in the 90th percentile, then they scored better than 90% of the people who took the test. That's basically it. I have this one for, I have this example. I'm sure as all of you know, because one of my teachers said they got the 51st percentile and they were always so happy about it, but don't try and be in the 51st percentile. Be better than that person. So 5-number summary. So you've got the minimum, the first quartile, the median, third quartile, and the maximum. Think of the minimum as 0, the first quartile is 25, median is 50, third quartile is 75, maximum is 100. So the 2 real different equations that they're going to ask you to like use this number for, like these numbers for, are going to be range, which is basically the maximum minus the minimum, or the IQR, which is Q3 minus Q1. So with that, I gave you a 5-number summary right here. So just determine what the IQR is. I'll give you guys a little bit of time to answer this. Quick on that. Yep. 14, because you just take the number 77, since that is Q3, minus 63, since that is Q1, and you get an answer of 14. So single box plot, this is what they might just show you something like this. Again, sorry, it's a little cut off. So basically what this is saying is you can kind of see the mean, you can see the upper quartile, you should be able to see the lower quartile, but sorry, it's a little cut off. Then up here where this is the maximum. the stuff past here is outliers. And if we were looking at it like complete, then down here it would have the same thing as up here, but it would just be a minimum and maybe a few more outliers. So there is an IQR method for identifying outliers. So basically what you want to do is using your 5-number summary, you take Q1, you subtract it by 1.5 times the IQR that you calculated. You take, to find the upper fence, you take Q3 and then you add 1.5 times the IQR. And then if there's any observation that is below the lower fence or above the upper fence, that is considered an outlier in this case. Scatter plots. So used to show a relationship between explanatory and response variables. It's a graphical representation of two quantitative variables. The explanatory variable is going to be on the x-axis. The response variable is going to be on the y-axis. So you always want to just consider what direction is it going, what form it has, what's the strength of the relationship, and are there any outliers? So correlation. This is a fun one. There's a lot of information. Don't let it get to you. Basically, it's just a measure of direction and strength of the relationship. So things you always have to keep in mind. It's always going to be between -1 and 1. It can't be any greater than 1 or -1. If it is, then there's an issue. If it's greater than 0, then there's a positive association. If it's less than 0, then there's a negative association. The closer to 0 it is, the weaker the relationship, and the closer it is to positive or -1, stronger the relationship. Correlation also has no unit, and the correlation between x and y will always equal the correlation between y and x. So here's a chart. I'm pretty sure I had this again later on just because this was in a new unit. So right here, if it's between 0 and 0.2, it's a very weak relationship. 0.2 to 0.4, it's a weak relationship. 0.4 to 0.6, it's a moderate relationship. 0.6 to 0.8 is a strong relationship. And 0.8 to 1, it's a very strong relationship. All right, simple linear regression, stuff that we've been working on recently that you just saw way back when. So basically, it's you use a straight line to predict the response variable using the explanatory variable. It doesn't really matter which variable is x or y, and they both have to be quantitative. It's y hat equals a plus bx. So y hat is the predicted value of y for any given of x. A is the y-intercept, and b is the slope. And this should look very familiar. Again, you guys have done this in the last lesson, but it also should be incredibly familiar because it looks exactly like the basic algebra equation of y equals mx plus b because it's completely derived from that. So that's why you can only really use it when it's linear. And so you also have residuals. So that's basically use a residual to calculate the difference between an observed value of y and a predicted value of y. So all that's saying is you want to take the actual value of y that you had minus your predicted value, and that's how you get your residual. So with that, all right, we're into review number 5, so I'll give you guys a little bit of time to answer this. All right, yeah. Looks like you guys got it. I'm just going to try and reiterate a little bit. So right down here, that's going to be your minimum. Right here, which is by about 105, is Q1. This line right here indicates your median. This line up here indicates Q3. And the top up here indicates your maximum. So if you guys said A, then congrats, you got it. So review number 6, which of the following has the weakest association? Sorry, these are all R values, so I'll give you guys a little bit of time to answer this. All right, yeah, you guys got it. Good. Just always be sure not to be fooled by negative signs, because it's basically the same as positive, just it's saying it's in the negative direction. So the closer it is to 0, the weaker the association it is, regardless of the sign. All right. So confidence interval and sampling distribution. Confidence interval is a range computed using sample statistics to estimate the unknown population parameter. Sampling distribution is distribution of sample statistics with a mean approximately equal to the mean of the original distribution, and standard deviation known as standard error. So confidence intervals, it's the sample statistic plus or minus margin of error, and the margin of error can basically be found using the multiplier times the standard error. So margin of error depends on the two different factors: level of confidence and value of the standard error, which is this. So for the 95% confidence interval is going to be 2 times standard error. And so it's basically just saying the number of standard deviations away it is from the mean. So for 68, the multiplier would be 1. For 95, the multiplier is 2. And for 99.7, the multiplier would be 3. If something not one of these numbers, then they would give you whatever that value is, or they would more than likely just give you the margin of error. So you always have to be careful looking at what have they given you, because there are times where they give you the margin of error, and then that can trip people up because they multiply it by the multiplier, or they give you the standard error and they think that is the margin of error. So just always be careful with stuff like that. So including confidence interval, all this stuff you've done before. I am however percent confident that the population, whatever the population parameter is in between the lower number and the higher number. So bootstrapping, it's a resampling procedure that uses data from one sample to generate a sampling distribution by repeatedly taking random samples from a known sample. It's also known as sampling with replacement. And so one thing to always be aware of is that some values may appear more than once and some might not occur at all. And whatever sampling distributions you make using a bootstrap also have to have the same sample size as the original. And then the distribution of the sample means is known as the bootstrap distribution. So impact of sample size on confidence intervals, just something to remember: as sample size increases, standard error decreases. Introduction to hypothesis testing. So you want to compute the probability that a population with a specified parameter would produce a sample statistic as extreme or more extreme than the one we observed. So the probability of that happening is the p-value. And if in the sample statistics vary from the specified population parameter to the extent that it is very unlikely that it would occur due to a simple random sampling error, we have to conclude that there actually is a difference due to the differences in the population. So hypothesis writing. This is all stuff that you've seen before, so I'm just gonna briefly go over it. So each test, you have the null hypothesis and the alternative hypothesis. So null always will basically say that there's no difference in the population. The alternative hypothesis states that there is a difference. And so just stuff to always remember when you're going in and writing what the hypothesis is. So ask yourself, what is the parameter being tested? What is the direction of the test? What is the value of the hypothesized parameter? And just know that's always written in terms of population parameters. So randomization procedures, so you want to construct a sampling distribution that can be used to make inferences about the population. And so it's going to be made assuming that the null hypothesis is true, so it will be centered around the null. Use it to find the p-value, and then from that you decide to accept or reject the null based on the p-value. Basically, your general alpha level is 0.05, so if p is less than that, then you can reject it. You can never accept the alternative hypothesis, and you always have to conclude in terms of the null hypothesis, and you just state in the rebel conclusion that we kind of went over before. So, all right, review number 7. I'll give you guys a little bit of time to go over this. All right, yep, seems like you guys got it, which is good. So the p equals 0.5. So, all right, next up, I'll give you guys a little time to work on this one. All right, you guys do remember all this stuff that we teach you. All right, next one. All right, so I'm just gonna go over this one. Most of you guys got it, but it's a little tricky. So the answer to this is D. It's hypothesis testing for a single mean. So it's asking what the average weight is. So that's how you know it's a mean. And it's also, since it's asking if it's different, that kind of gives you a hypothesis. If it was just asking what is the average, then you'd probably be using the confidence interval. So, all right. So next up, we have type 1 and type 2 errors. So basically, when you're conducting a hypothesis test, you only have 2 real decisions. You either reject the null or you fail to reject the null. You don't know if it's necessarily correct, but you only base it on like what data we have. So when you're rejecting the null hypothesis, you have 2 real outcomes. So there could actually be a difference in the population, in which case rejecting the null was the correct decision, or there might not be a difference and our sample is wrong, so an error was made. when you're failing to reject the null hypothesis, you could either do the correct decision where the null hypothesis is true and there was no difference, or perhaps there was a difference in the population, but it was not rejected, in which case an error was made. So, handy little table that was you guys have seen before, and I'm sure you've seen it plenty of times, but it's good to have. So basically right here you have your decision to either reject or fail to reject. Then over here in reality, if the alternative is true or if it is wrong. So if you reject the null when the null is true, then you made a type 1 error. If you fail to reject the null when the null is wrong, then you made a type 2 error. Power. I don't really think any of you guys have seen this at all, so I don't really think it's worth that much going over. But again, just want to make sure. So it's a probability of rejecting the null given that the null hypothesis is false. So it's just 1 minus beta, where beta is the probability of committing a type 2 error. And all right, we're into review number 10. So I'll give you guys a little bit of time to go over this. Honestly, I would have accepted D because I'm pretty sure we're all feeling this right now. But as you guys got, the answer is in fact D. So good job. Yeah, I think we're only about halfway done, so we just gotta keep trucking along, guys. So reading number 11, I'll give you guys a little bit of time to answer this one, and then we'll keep on going. All right, well, you guys are right. It is A. And unfortunately, I don't really have too many more pictures of my dog because she's going in for surgery on her jaw soon. So sorry about that. But don't worry, on Sunday, I'm pretty much just going to have only pictures of my dog up. And so we can all just go and cry about finals together because it's awful. But yeah, no, you guys are right. It is a type 1 error. So because you rejected the null, but there was no difference, so you committed type 1 error. Good job, guys. All right, so with this, now we're on to material past, post midterm 1. So welcome to midterm 2 stuff. We're officially like halfway there, so just gotta keep on pushing, guys. So, all right, binomial random variables. So it's just a specific type of discrete random variable that counts how often a particular event happens in a fixed number of trials. So the conditions for this to happen is that there has to be a fixed number of trials, or fixed sample size. The probability of success has to be the same for each trial, and the trials are independent of each other. So just think flipping a coin. That's just your go-to, guys. Flipping a coin. So the central limit theorem. So this basically just answers when can sampling distribution from mu be estimated using a normal distribution. So if you have a sample size of at least 30, the distribution of means will always be approximately normally distributed, regardless of the shape. And so that means that the mean of mu, and you'll get a mean of mu and a standard deviation of that. So basically all it's saying is standard deviation equals standard deviation divided by the square of the sample size. All right, so computing mean and standard deviation. So your mean equation is the expected value of, so your formulas to calculate the mean, you've got the sample size times probability of success. To calculate the standard deviation, you've got the square root of the sample size times probability of success times, in parentheses, 1 minus the probability of success. So with that, we go into this next question. So I'll give you guys a little bit of time to answer this. All right, I'm gonna go over this. I hope I didn't catch you guys off guard with anything. If any of you are ever confused, please just ask questions. But yeah, so your probability of success is 0.53. You get that from the equation of the mean equals the sample size times p. So you just rearrange that to the mean divided by the sample size equals p. So it's 8 divided by 15 equals p. So you get that. And then to calculate the standard deviation, it's just the square root of n times p times 1 minus p. So it's just the square root of of 7.97 times 0.47, so you get 1.93. So good job if you guys got it. All right, so next up, I'll give you guys a little bit of time to read through this and make your decision. All right. Finally got you guys. All right. So the answer to this is no, you cannot use the binomial round distribution, basically because you don't have the fixed sample size. There might be a few other reasons, but this is the main one that like should just be glaring in the face, is that you're planning to go until you lose all your money, betting $10 each time. However, there might be times where you earn, you win some of the games, and so that would increase the sample size. Well, there might be times where you just lose each and every single one. So, yeah, I gotcha. So you just always have to be careful about that. I highly doubt there's going to be a question like this intense on the final, but that's right. That's why you can never gamble, because you'll never win. All right. So just gotta keep chugging along, guys. So lessons 8 and 9, just combine them into one. So it's just inferences for 1 and 2 samples. So going back to what I said earlier, independent variables not related, dependent or matched pairs. They are like matched to one another. So, all right. Yeah. So I'll just give you guys a little bit of time to answer this one. All right, looks like this was the redeeming question. So good job, guys. All right, so for rule of sample proportions, basically it's saying when can you use P, when can P be estimated using a normal distribution? So it's saying that if it's normally distributed, okay, so long as you have n times P is greater than or equal to 10, and n times 1 minus P is greater than or equal to 10, you can assume that your proportion is normally distributed with the mean equal to P and a standard deviation of equal to the square root of P times 1 minus P divided by sample size. Lost my ass again, sorry. All right, so hypothesis testing for a mean. I'm going to make a deal with you guys. I'm just going to show this table once, and then every other time it pops up, I'm just going to skip it because it's all the same, and I know you all get tired of it. So when you want to check the assumptions or hypotheses, so the data has to be quantitative and randomly sampled from a population, so that is approximately normally distributed. So for your research question, the null, it's always going to say that it's equal to. The alternative is going to say, is it different? So if the mean is just strictly different, then it's a not equal to sign and it's two-tailed. If you're asking, is the mean greater than the null mean, then it's greater than sign and it's right-tailed. And if the mean is less than the null, then it's going to be a less than sign and left-tailed. So then you want to calculate the test statistic. sorry. In most cases, mu is going to be 0. I kind of said it will always be 0, but I will just say like most cases, because there might be one or two times where it will say that if the null is different than something. However, assuming that the null is 0, that's how you kind of like calculate this, where you just use this equation where x bar is the sample mean minus the hypothesized mean divided by the standard deviation divided by the square root of the sample size. All right, so just going to go over the assumptions for paired means. So basically, data has to be paired. The difference between the two groups must be normally distributed in the population, or sample size has to be at least 30. So then test statistic, exact same one as the one that we just saw. I'm just going to go over it again real quick. So x bar, sample mean, minus the hypothesized mean divided by standard deviation divided by the square root of the sample size. All right, so for two independent means, the assumptions are that the data is independent, that both populations are normally disputed, or greater than or equal to 30 again. All right. And then test statistic, it's more annoying, but basically it's the mean of 1 minus the mean of 2 divided by the square root of the standard deviation squared of 1 divided by the sample size plus the standard deviation of 2 squared divided by the sample size of 2. All right, so hypothesis testing for two independent portions. The assumptions are is that there have to be a minimum of 10 successes and 10 failures in each group. So for your test statistic, it's p hat 1 minus p hat 2 divided by the standard error. Then the standard error is technically p hat times 1 minus p hat times 1 divided by the sample size of 1 plus 1 divided by the sample size of 2. All right. You guys didn't see that. So I'll give you guys a little bit of time to see this, to answer this one. Sorry. I guess my fingers are a little trigger happy right now. All right. I thank you guys for taking your time and probably doing this one, even though I did show you the answer, because it is a, so you just go with the square root of the proportion times 1 minus proportion divided by the sample size. And once you plug in all those numbers, you do get 0.329, 0.0329. So read number 16. I'll give you guys a little bit of time to answer this one. All right, so I'm going to go over this. So it's in fact D. Good job if you guys got it. So the reason why it's D is because it's asking about the averages between two different groups. So with that, you can kind of like cross off proportions and you can cross off one sample mean. So you're kind of left between, is it paired or is it independent? The reason why it's independent is because the outcome of one does not affect the outcome of the other. So, you know, how the adult learners do doesn't affect how the traditional students do. So that's why it's independent. So good job, guys. All right, more questions. Yay. So I'll give you guys a little bit of time to answer this one, then we'll go over it again. All right, yeah. You guys are getting it. So it's in fact D with the scatter plots. And so the reason being is because it's asking about the relationship between two categorical variables. It's asking about how much they ate and how much they burned. And so the other ones, pie chart, is only one categorical, histogram is only one quantitative. And then the cluster bar chart is just several categorical. So the scatter plot is the only one that can work for you. All right. So next question. I'll give you guys a little bit of time to answer this one, then we'll go over it again. All right, yeah, so we're going to go over it. So it is in fact A. So it's the sample statistic that we have here minus the hypothesis. This is one of those cases where it's not zero, divided by the standard deviation, and then divided by the square root of the sample size. So you plug all that in, and you get 2.48. So. Yep, that would do it to you. All right. Yep, just always got to be careful between whether it's asking for a standard error and standard deviation, because it can really mess you up when you're trying to do it. And also, guys, I will apologize that these are all kind of like questions that you've seen before in previous reviews. I didn't get any new ones for the final. Honestly, I'm not even entirely sure if I'm supposed to be like, if I was supposed to do this review, because I never got any notifications, but I just decided that regardless of whether it was or not, I just wanted to try and get you guys as prepared as possible for the final. So if the questions seem like they popped up before, they have, but I'm just trying to do my best to help you guys. So, all right. So one-way ANOVA, really short section. It's basically like the alternative to using a bunch of t-tests, because if you did want to use a bunch of t-tests, then you just need to use a lot of them. you would increase the chance of getting a type 1 error, and you could possibly inflate the alpha. All the while, it wouldn't really provide information about the independent variable overall, so it's using a bunch of t-tests isn't great. So basically what hypothesis testing with ANOVA is. So first, you want to just check your assumptions. So the assumption is that each sample is independent and random. The distribution of the response variable follows normal distribution, and the population variances are equal across the responses for the groups. So the null is going to say that all groups are equal. The alternative is going to say that not all groups are equal. The F value, which is found in, which you use in Minitab, which again, since you're not really going to be using Minitab on the exam, I'm just going to give it to you, can be used to find the p-value. So, all right, with this, we go right into our next question. So I'll just give you guys a little bit of time to go over this. All right, yeah, you guys got it. So it is in fact C. The null hypothesis is rejected because the p-value that we got was less than 0.05. So that means that the population means are different. All right. So the goodness of fit test. Sorry, we just moved past the last midterm 2 stuff. So now we are on to the last like 2 weeks of what we've done. So we're really nearing the end, guys. Just a little bit further, and then we'll be done. All right. So this is basically going with the chi-square test. So the goodness of fit test, it's basically what the chi-square test is. It's basically conducted when there's one categorical variable with more than 2 levels. So if the expected counts are all at least 5, then you can use it. Then the expected count will equal the sample size and multiplied by the hypothesized proportion. If it's not 5, then you pretty much have to use randomization testing. And so for the goodness of fit test, basically you compare the observed counts to the expected counts. The observed counts are the number of cases in the sample of each group, whereas the expected counts are computed giving the null hypothesis is true, and the number of cases we would expect to see if the null was true. So for the chi-square distribution, varies depending on degrees of freedom. So the degrees of freedom equal number of groups minus 1. And then to find the p-value, we find the area under the chi-square distribution to the right of our test statistic. Yeah. Sorry, I'm pretty sure that's wrong. Yeah, it should be like number of columns minus 1 times number of rows minus 1. Sorry about that, guys. So hypothesis testing, the assumptions are that the null hypothesis contains the equalities, and the alternative is the one that at least one proportion is not specified in the mole. and that that's the hypothesis. And then the assumptions that all expected counts must be at least 5. And then this is how you calculate the test statistic, where it's the chi-squared obtained is equal to the sum of the observed score minus the expected score squared divided by the expected score. So continued, all stuff that you've seen before. Basically, you find the p-value, you make your decision, then you just address the irrelevant conclusion. So chi-squared test of independence. So it's used to test the relationship between two variables. So computes expected values for cells in two-way contingency table under the assumption that two variables are independent. So the assumptions are that all counts must be at least 5. The sample is randomly distributed. Randomly drawn from the population. The null hypothesis that there's no relationship, and the alternative. Oh, wait, no, sorry. I'm tired, guys. So this is right. Degrees of freedom is just number of groups minus 1. For this is actually the row till times the column till divided by n to find the cell frequencies. And then test statistic is the same as before. And then this is the degrees of freedom. Number of rows minus 1 times number of columns minus 1. Sorry, guys. It's been a long day. I'm sure all of you can relate. All right, so relative risk. It's compares the risk of one group to that of another. So, risk of group 1 divided by the risk of group 2. So going all the way back to like when we talked about, the flu way back when. And so let's say that the risk of a child getting the flu is 45 out of 100, and the adult risk is 0.1. So then it would basically be written as so children are, 0.45 divided by 0.1. So it's 4.5 times more likely than adults to get the flu. That's relative risk for you. All right. So next up, I'll give you guys a little bit of time to answer this. If any of you get it wrong, I base it solely on myself. I'm sorry that I confused you guys a little bit. I confused myself. It's just been a long night. All right. Yep. Is in fact 3. Good job, guys. Sorry if I confused you all again. So basically, for the chi-square test of independence, when you're calculating degrees of freedom, it's number of rows minus 1 times number of columns minus 1. So in this case, it would be 2 minus 1 times 4 minus 1, which would get you 3. All right. So I'll give you guys a little bit of time to work with this, and then we'll go over it. All right, yeah. So in this case, the correct answer is in fact A, because it's total number of rows times total number of column divided by n, the sample size. So just going back from this, so it's asking about non-smoking females. So it's the 728 times the 589 divided by the sample size of 1033 to get 410. And yes, it could technically be 411 rounded up because the answer you do get is 410.5. However, I just put 410. So sorry. All right. So correlation. Whew. Sorry, guys. We're so close. So close. So your assumptions that both variables quantitative. So to calculate your test statistic, you gotta be using Manytab, but since it's the exam, they probably just gotta give it to you for your p-value. So it will give you a p-value for a two-tailed test. If you need to get it for one-tailed, then all you have to do is just divide that by 2. Then you make your decision and you save that real conclusion. So your assumptions of simple linear regression are that it's linear. For the independence of errors, basically there's like no relationship in the errors. The correlation for the errors is about 0. The errors are normally approximated, that there's like equal variance, that there's no real pattern in the errors. So the confidence interval for a slope, it's B1 plus or minus the T multiplier times the standard error of B1. So B1 is just your sample slope. The T multiplier is the value from the T distribution with degrees of freedom of n minus 2. And then you just have the standard error. All right. And I know this was one that a lot of people missed on their quiz, so we're just going to go over it. So the coefficient of determination is basically the amount of variation in the response variable that can be explained due to the explanatory variable. So basically, you just take whatever the R value that they give you, and you just square it. And that's it, guys. So hopefully this will just be easy points on your final and not something that, comes back to get you. So just stuff to always be aware of. Outliers, they can change the correlation. They heavily affect the graph. So just be careful. And extrapolation, you can't use the data for something else. So basically, if you create data going from a certain latitude in like the US, so say you're going from like Philadelphia up to New York, and you're getting the average temperature for cities in that range, you can't use that for a city of a different latitude. You can't really use that for something like down in Miami because it won't really fit the data. All right, so these are just some of the last few review questions. So I'll give you guys a little bit of time to go over this. All right, so I'm going to go over this. I will just say that you're only using the equation. You're not really using, you're not graphing it out. So I feel like that might confusion. The answer is C, because you can't really determine whether or not the graph is linear or not based only on the equation. You have to kind of like see it graphed um, to predict the value of y in a particular given value of x. That's what the equation is all about. And then to estimate whether it's positive or negative can be found using pretty much the equation. You can just like determine that. And then to estimate the slope, it just requires a little bit of manipulation. But if you know what y is and you know what x is, you should be able to figure out what the slope is. So the only one that you can't really do is just discover whether the association is linear or nonlinear. Right. So next up, just using the regression equation. So I'll give you guys a little bit of time to go over this, and then all right, yep. All I have to do is just plug the 67 into x, and that's how you get your predicted value of y. All right, so I'm pretty sure this is the last question for the night. So just be sure to end up on a good note, guys. So give you guys a little bit of time to go over this, and then almost done. All right, so the answer is indeed A, because again, you just take the R value and you square it. So in this case, just wrote it out of negative 0.8 squared, so negative 0.8 times negative 0.8, and you get positive 0.64, which is 64%. So yeah, pretty much like you're never going to get a negative percent when you're doing the R squared, just because it's not really possible. So yeah, that's just some stuff to take away. With that, we're done. So thank you guys for coming out and listening to me like lecture at you for about an hour and a half. I know this wasn't exactly fun, but I hope that you guys got something out of it. I hope that you guys feel a little bit more prepared. If your calculator does a negative value squared to a negative, then there's something wrong with your calculator. That's weird. Anyway, good luck on your stat final. Good luck on any other finals that you have. I know you guys are going to do really well. If you have any questions, let me know. I'm here for you guys. I'm going to be doing the exact same, review on Sunday. More or less, it might just be more pictures of looking at dogs and trying to, get ourselves pumped up a little bit. And, thank you guys for supporting me this semester. I hope that everything I've done has helped you. It certainly has been a ride, and I hope that you guys do well in this class and beyond. So Thank you guys, and if I don't really see you guys again, good luck on your final. Have a good Christmas. If you're Jewish, happy Hanukkah. It's a little late, but still happy Hanukkah. All that stuff, and have a good one, guys.